Hi, welcome to our second lesson. Today we are going to perform the first fluid flow simulation, and what we are going to do is we are going to simulate the potential flow over NACA 0012 airfoil. As most of you probably know, potential flow is the most basic type of flow model, so this probably will not have very big practical implications for your simulations, but we think it is very nice to show on this very simple example what is the idea of performing simulations in this MATLAB Toolbox. So let me remind you that the potential flow is defined by assuming that the velocity can be casted as a gradient of a potential field. And secondly, you know that you deal with an incompressible fluid flow, so divergence of velocity must be zero. If you substitute this equation into that, you end up with the Laplace equation for the velocity potential field. The proper boundary conditions, if you want to have the flow which is coming from this direction, you need to specify a Neumann boundary here with the Neumann condition for phi, and let me say this will be 50 meters per second. On the outlet boundary, you have to define the potential value, so we say it would be simply zero. You can always assume every other constant. It will have absolutely no implications since velocity is defined as the gradient, so even if you define a different constant, this will also be fine. We need to figure out what the boundary condition for all the walls is, and for a solid wall, well, the velocity does not penetrate a solid wall, so you have to specify zero homogeneous Neumann boundary condition, and you can do the same at some channel walls which are pretty far from the airfoil. That's also correct. So, all right. So now let's summarize this. What do we have to do? We have to solve a Laplace equation and assume these boundary conditions. For the Neumann boundary condition, a flux boundary condition, zero Neumann boundary condition, and zero Dirichlet boundary condition. What we do is we go to MATLAB right now. I have the whole script already written for you, but we will describe it step by step. So what we do at the beginning, we simply cleared the workspace and the comment window, and then, as usually in every CFD solver, what you do, you have to import a mesh. P, E, and T will be variables that store mesh in our QuickerSim CFD Toolbox. Without going into the theory of the data structures and without going into the details, simply remember P, E, and T usually denote all the data which store the mesh. P is something which will be important. These are coordinates of all the nodes in the mesh. So P array simply defines the locations of the mesh nodes. Alright, so we call import mesh gmesh function, and you have to download this file, the mesh file we have already created for you in gmesh, and upload it to Facebook, so please simply use our mesh. What is important, you can find, after downloading our toolbox and documentation, you can find a link to another tutorial on geometry creation, so that's why we do not cover geometry creation in this very simple Facebook course. If you are interested in geometry creation in gmesh, simply refer to the links that you have obtained during registration process. what is important is we have somehow to define the inlet boundary, and this will be you can denote the boundaries on the physical line IDs that you have created in Gmesh. So please remember, creating physical line gives a certain physical ID. Inlet has got 9, our airfoil has got 11, and outlet boundary is 10. So please simply keep in mind these IDs. All right, we are going back to MATLAB. We have said that we need to solve a Laplace equation, so basically a diffusion problem. So there is nothing else what we need to do. We simply assemble the diffusion matrix. We will assemble a linear system of equations based on the finite element method. The arguments that we need to pass to this assembled diffusion matrix function is information about the mesh P and T arrays. It is not needed at all at this moment. And one is diffusivity. Basically, for a diffusion problem, you need to define a diffusivity, because we are solving a very simple Laplace problem. Then our diffusivity is simply equal to 1. And this assembles D, diffusion matrix, and F, right-hand side vector. Alright, so we have told the toolbox that we want to solve a diffusion problem. Now what we need to do is we need to define boundary conditions. We do it by the following statements. Impose scalar boundary condition to D, P, E, again mesh, D, matrix, F, right-hand side vector. 9 denotes the physical line ID, which means that we want to do something here on the inlet. And we want to specify Neumann boundary condition, which is called flux in our CFD toolbox. And this flux please notice that you want to have 50 meters per second in this direction, so from left to right, whereas normal vector always points out of the domain. So for having plus 50 meters per second along the x-axis, we need to specify boundary condition minus 50. And on physical line 10, so at the outlet, we define value boundary condition, so basically the Dirichlet boundary condition, which is equal to 0. And the two arguments that are modified during the call to these functions are D, the matrix, and F, right-hand side vector. Then we need, after we have assembled the diffusion problem and imposed proper boundary conditions, we have to solve the system of linear equations for phi. So we simply call the usual MATLAB function. And what we do later is we want to check what the velocity field is. So for a velocity field, please notice we need to compute a gradient of phi. That's pretty easy. V, velocity, equals solution gradient to D, to PT. This is the mesh. We need to know on what kind of mesh we want to differentiate. We want to compute the gradient, and we pass the phi field. Basically, in airfoil simulations, we are interested in the velocity magnitude around the airfoil and the pressure coefficient. So these are simple MATLAB MATLAB comments. If you want to compute the magnitude, simply take the square root of, and this is important, V. After you call solution gradient, this will return you velocity for each node, and the first column will give you x velocities, and the second column of the gradient will give you y velocities. So basically you take the square of vx plus square of vy and take the square root. This gives you velocity magnitude. If you want to compute pressure coefficient from the basic formulas of aerodynamics, you can find that Cp would be equal to 1 minus v minus magnitude of velocity squared divided by the free stream velocity squared. Because our free stream value was 50, we simply take the square of this velocity. And at the end we want to plot these values. We want to plot the velocity field and the pressure field. So we open a new figure, and the function display solution to D is the usual function which is present in the toolbox to display scalar fields. And again you have to pass P and T information about the mesh. Cp is the field which is defined for every node in the mesh, and this is simply your description that you want to give to the plot. This will be pressure coefficient. Again, the same way in the second figure, but right now we want to specify Vx, not the magnitude, simply Vx, and that's it. Let me run this part of the script with F9 button, and you can see what you get. You get the pressure coefficient field and you get the Vx field. What you are usually interested in airfoil simulations is what is the pressure distribution along the airfoil. So this is where we go to basic post-processing. If you want to learn more about post-processing, please refer to tutorial 1 in our documentation. Then you will have all this information given step by step. But basically what we need to do is to plot the pressure values, the pressure coefficient values at the mesh nodes which are lying on the airfoil. So you need to, if you knew what nodes are lying here, this would be easy to do it with a simple plot command in MATLAB. Alright, so we need to figure out what nodes are lying on this airfoil, and we do it by this function called airfoil nodes equals extract node IDs on edges, and by call to this function you extract all IDs of nodes that are lying on your edge 11, and edge 11 is our airfoil. And then you can plot it with usual MATLAB function, whereas scatter does basically the same what plot does, but it only displays user points. And what we would like to have is I first show you the plot and then explain what we have done. Basically what we want to have is we want to have the x over c, x over chord, so the location along the airfoil on one axis, and on the second axis we would like to have the pressure coefficient. Alright, so we do scatter at, and as I said, P denotes coordinates of nodes in the mesh. 1 denotes this would be x coordinates. 2 means we would like to plot the y coordinates, and we only want to do it for airfoil nodes. After call this function, you see that airfoil nodes gives information about IDs of nodes that we are interested in, and the same here. We want to plot a pressure coefficient, but only for the nodes which are lying on the airfoil, and then just get a title, X label, Y label, and turn on the grid. So let me run the script again with F5. So you can see by doing this the velocity field, you can see the pressure coefficient field, and what is probably most interesting is you get this pressure distribution. And if you look at some reference data, you can find that for zero angle of attack, the reference data, well, is exactly the same. You can see minus 0.4. Here is dropping to around 0.2. Here again 0.2. So really this pressure distribution, which is simulated with a very simple potential flow model, is accurate for this simple application. Thank you for this second lesson. In the next lesson, we are going to simulate the 4 Navier-Stokes equations. So see you then.